All right, welcome to today's Explainer. We are unpacking something absolutely fascinating, a massive sequence of breakthroughs in artificial intelligence. We're looking at exactly how today's incredibly powerful AI models process language and, well, understand sequences. If you've ever interacted with a modern large language model, you've definitely experienced this firsthand. But today, we're really going under the hood. Using source materials from some top computational lectures, we're going to visualize the actual mechanics of how machines learn to read, remember, and speak. Okay, let's dive right into this, because it really sets up the core mystery of modern AI. You know when a machine just seamlessly finishes your sentence or generates a brilliant essay out of nowhere? How does it actually know which word to output next? It feels like magic, right? But as we'll see, it is purely a mathematical game of predicting the future. And predicting the future inherently requires a deep, highly structured understanding of the past.
To wrap our heads around this, we gotta look at what's called the sequence problem. Imagine I just show you a ball suspended in midair and ask you, hey, where is this going next? You can't tell me. It's a completely random guess. But if I give you the sequence of its past trajectory, where it was 1 second ago, 2 seconds ago, well, suddenly the prediction becomes totally clear. Text works exactly the same way. The word deep by itself is super ambiguous, but if the past trajectory of the sentence is introduction to neural networks and predicting the word deep followed by learning becomes pretty obvious.
But here's the catch, right? Neural networks can't actually read English. They only crunch numbers. So how on earth do we feed a sequence of words into a machine? Well, first, we take our text and we chop it up into smaller pieces called tokens. These can be whole words or even just parts of words. But we can't stop there. We then translate those tokens into embeddings. This is exactly where the machine transforms human words into these sprawling numerical representations that it can actually calculate.
And honestly, embeddings are completely mind-blowing. They aren't just random numbers thrown together. We're talking about high-dimensional vectors where physical directions literally encode semantic meaning. Imagine this massive multidimensional spatial map. Words with similar meanings naturally cluster together. You can actually do math with concepts here. Like if you take the numerical embedding for the word king, subtract the mathematical direction for masculine, and add the direction for feminine, the closest point in that space is the word queen. It's incredible. The AI literally maps out human concepts through geometry.
Moving on to Section 1, the first solution, recurrent neural networks.
So, once we've mapped all our words into numbers, how do we actually process them in a sequence? Well, for years, the absolute gold standard in artificial intelligence was the recurrent neural network, or RNN. The genius of the RNN is that it maintains an internal state or memory. Instead of processing every single word in isolation, an RNN uses a recurrent loop. It updates a hidden memory variable at every single time step. It reads a word, updates its memory, reads the next word, updates its memory again, and carries that constantly evolving context forward.
And this brilliantly illustrates exactly how we process information as humans. Think about reading a good book. In step 1, you read the current word. In step 2, your brain just naturally combines that new word with your memory of the story so far. Then in step 3, you anticipate what comes next. RNNs simulate this perfectly. They process sentences word by word, continually mixing the present input with their past memory.
But as elegant as that sounds on paper, it led to a pretty massive, fatal flaw, the encoding bottleneck. Imagine you're reading a massive 1,000-page novel, but you're only allowed to keep a single, fixed-size index card of notes for the entire thing. By page 500, you are definitely going to run out of space, and older details are just going to get overwritten. RNNs try to squeeze an entire paragraph's history into a single internal memory state, and eventually the system just chokes. The consequences of this bottleneck are, quite frankly, devastating for large-scale AI. First off, the network forgets long-term dependencies. If a pronoun is separated from its noun by, say, 50 words, the RNN just loses the connection. Second, it suffers from vanishing gradients. Multiplying small numbers step after step means the mathematical signal of that past memory just vanishes into thin air. And third, because it has to read step by step, you absolutely cannot parallelize the computation, which means it is agonizingly slow to train. This perfectly captures the evolutionary leap we desperately needed. RNNs are essentially stuck in traffic, processing word by word, slowly bleeding memory over time. To fix this, AI researchers realized they had to ditch the step-by-step method entirely. Enter transformers. They process all the data at once, making them massively parallel and blisteringly fast. A real game changer. Which brings us to Section 2, The magic of attention.
But wait, if you process an entire paragraph simultaneously, instead of in chronological order, how does the machine actually know which words relate to each other? Well, the answer to that changed natural language processing forever. Back in 2017, researchers at Google published a paper with a title that sounds more like a Beatles song, but has since become truly legendary in computer science: Attention is All You Need. They proposed discarding recurrence entirely. No more step-by-step reading. No more hidden memory states. Just looking at all the data at once and letting the words figure out how to mathematically attend to one another. To really understand how attention works, we can use a pretty brilliant analogy from our source material, a YouTube search. Think about it. When you search for a video, you type in a query. The database then compares your query against the keys, which are the video titles. When it finds a match, it returns the value, which is the actual video you want to watch. The attention mechanism in AI uses this exact query key value system, but it uses it on the words themselves. Now, what's really interesting about this is how that exact search concept applies directly to grammar. Take the phrase, "a fluffy blue creature." When the model reads this all at once, it doesn't initially know what the word fluffy refers to. So the word creature effectively acts as a search term, a query, looking backward through the sentence for adjectives that describe it. So here's how the math actually breaks down. The token creature acts as our query. Mathematically, it's asking, hey, are there any adjectives before me? The tokens fluffy and blue act as the keys. Their vectors mathematically answer, yes, we are adjectives. The network then computes the similarity between these queries and keys using dot products. When they align perfectly, it extracts the value, updating the basic token of creature into a highly specific vector representing a fluffy blue creature. The words are literally talking to each other.
Now, to make sure a word doesn't get completely overwhelmed by too much information, the network applies something called the softmax function. Softmax takes all those raw mathematical dot products and seamlessly converts them into legal percentages, or weights, between 0 and 1. It basically dictates exactly how much attention one word should legally pay to another. If creature finds fluffy, softmax might assign an attention weight of 0.9, locking those concepts together while totally ignoring irrelevant words.
Let's see how this builds, because it turns into an impossibly complex web of understanding. The network doesn't just do this search once. Oh no, it runs multi-headed attention. One head might track grammar, like we saw with adjectives to nouns, but simultaneously, a second head tracks pronouns to antecedents. A third might track high-level poetic tone. Dozens of these attention heads are running simultaneously, allowing the AI to grasp deep, multi-layered contexts in a fraction of a second.
And that sets us up for Section 3, Why Transformers Rule AI.
This mathematical shift from sequential reading to parallel attention, it completely dismantled the bottleneck of old AI. I mean, it literally paved the way for the generative AI boom we're seeing right now. And these advantages are the secret to massive scale, because transformers don't read step by step. They can process mountains of data in parallel. During training, we can use masking, hiding words in a huge document and forcing the model to predict thousands of them simultaneously. This completely parallelable architecture perfectly maximizes modern GPU hardware, which is custom-built to do exactly this kind of massive simultaneous matrix multiplication.
So the absolutely crucial point here is the sheer scale this allows. 12,288. That is the number of dimensions in the embedding space for massive models like GPT-3. Because of the transformer's efficiency, we can map words into over 12,000 dimensions. Think about that. This allows the AI to hold tens of thousands of complex associations, tones, and facts, like, knowing that Michael Jordan plays basketball, all encoded in a massive geometric space and updated instantly through attention. Which really leaves us with this final, kind of provocative thought. We've seen the mechanics, right? We know it's all queries, keys, and 12,000 dimensional matrix math. But if a machine can perfectly predict the next word, flawlessly tracking grammar, context, and poetic tone using these massive attention patterns, is it developing true understanding? Or is it simply the most highly advanced pattern-matching engine humanity has ever built? It's a huge question, and one that top researchers are still debating today. Thank you so much for joining me on this explainer. I really hope this deep dive has forever changed how you see the text popping up on your screen. Keep learning, and I'll catch you next time.